Thank you, all of you joining us today. I know it's a busy time of year, so we do appreciate you taking time out to catch up on what's new in data exchange standards. Today is the second in a series of 3 webinars that we'll be holding on the topic of trusted data. Jay has been giving these presentations at the PNEC conference. This particular one we're showing today was given at PNEC 2018. And you will see on our calendar, August 8th, we have part 3 of this series that will be our next webinar. As you know, Jay Hollingsworth is our CTO and has a long and deep experience in the area of data management. And this aspect of trusted data is one that he raised together with our community and is one that is getting a lot of attraction and attention in the industry today. As you know, our webinars do not allow for immediate participation during the presentation, but there is a Q&A system that is active, so you can submit questions during or after Jay's talk for us to discuss once he's finished. This webinar is being recorded, so you will be able to pick it up and replay it and share it a day or 2 after it takes place. It will be on our website in our library. So without further ado, again, thanks for joining us. And Jay, I will hand over the microphone to you for your presentation. Thank you.
Thanks, Phil. Can you hear me okay?
Yes, I hear you okay.
Great. All right, good morning, everyone. And welcome to the webinar, as Phil said. So this is part 2 of what turned into a 3-part presentation about trust and trust in data. So we'll go ahead and get started. We're going to, in this webinar, give a quick summary of what was in the first webinar so that you sort of understand what we mean by trustworthiness and ways of trying to quantify actually trust. And then we're going to delve into a specific example of a kind of data that you could apply some sort of numerical scoring to if you chose to determine the trustworthiness of a particular piece of data for a particular purpose. And the kind of data that we're going to talk about is measurements. We make lots of measurements in the oil field with wireline tools or sensors on surface equipment like drilling rigs or producing wells. So we're going to talk about that as an example of a kind of data and then discuss the sources of uncertainty in that kind of data and how that leads to a lack of trust on behalf of users who use that information and what data managers can do to improve the trustworthiness of that information to the people that use it. So that's what we're going to cover this time. So to go quickly through the question of trust, last time in the first webinar, we spent the entire webinar talking about different ways to measure trust and think about trust. And it all stems from the original article where the notion was put forth that geoscientists spend 60% of their time looking for data. And this is the little graph from the original article. Of course, it shows that people spend 5% of their time in coffee breaks and 5% of their time in meetings and presentations, and they spend 60% of their time looking for data. And we more or less proved in the previous webinar that that isn't really so, but they are spending 60% of their time doing something other than what they think they should be doing. And the truth is, geoscientists and, in fact, many knowledge workers in every field spend a lot of time gathering data, doing what they call wrangling or munging their data, fixing coordinate reference systems, fixing units of measure, trying to understand why the left half of the field somehow is different than the right hand of the field, and all of the kind of typical things that we're accustomed to. But this information, this work is not a waste of time. As you're working through the data, you start to get a feel for it, and insights often happen before you've even started doing your interpretation or your analytics, whatever your job is. And insights often come out of this data munging kind of work. So it's not really a waste of time, but it's also not time spent, beginning to do a particular interpretation or processing or analytics task. But the key point from the previous presentation is that knowledge workers will take as long as they need in order to reach a set of data that they believe they can trust. Knowledge workers are the kind of people, they don't want to do their job unless they trust the data they're working with. So if it takes a week, if it takes a month, if it takes 3 months, they will spend the time that's needed to build that trust in their data. So anything that we can do as data management type people to make the data more trustworthy means that the knowledge workers will spend less time doing this data munging, because they will simply trust that the values they're getting out of their data environment can be used straight away. Another point that we made that we want to reiterate here is that trusted data is not the same thing as high quality data. So you know that the gas gauge in your car is not terribly accurate. Everyone knows how far below the E the needle can go before they're really, truly out of gas. But in spite of the fact that you know the gas gauge is low quality data, when it gets somewhere near the empty mark, you pull into a gas station. So basically, you're acting on data that is known to be of low quality, but you act on it because you know it's low quality. And you say, well, this gauge isn't terribly accurate, so I'm going to go ahead and pull into the gas station. So you use the data for the purpose that's intended, which is deciding when you need to fill the tank, in spite of the fact that you know that it's low quality, but you can still use it. On the other side, people have very little trust that food, the calories given for food, are correct. Nobody can believe that a hamburger is really that many calories, or a beer is really that many calories. But in fact, it's really precisely measurable, and the data are very accurate. But people don't trust it. So that's the other extreme, that just because data is high quality doesn't mean that people trust it. And the little picture on the right, incidentally, is a bomb calorimeter, which is the instrument that's used to measure the calories in food. The other thing about trusted data is trusted data isn't the same as complete data. There are many kind of business rules that are written that say that, well, I can't trust this data if I don't have a latitude and longitude, or I don't have, some other piece of information about this particular entity. But the truth is, we make decisions all the time on incomplete data, and the fact that a particular piece of information is missing doesn't invalidate an entire data set. It just means it's useful possibly for a different purpose, but the key thing for the users is to let them know the data is incomplete. If a user downloads some data and they believe it's complete, and then they find it's incomplete, then they lose trust in that source of data. If the source of data told the user, here's the data we have, and oh, by the way, it's missing some aspect, at least the user can trust that the source of data has correctly disclosed what the flaws in it are. And it enables that user to decide whether the data set's useful for the purpose they want to put it to. So basically, trusted data is different. And then, of course, we have the least trustworthy piece of equipment in existence over on the right. So the dimensions that we talked about in the first webinar were 3 dimensions. The first dimension of trustworthiness in terms of scoring something is, do we trust the source of the data? Is it our official company source? Have I used it before and it has a good reputation? The second is, do we trust the handling the data has experienced? So if it's calculated data, do we know what equation was used? Do we trust that it was done correctly? Do we trust the software that implemented implemented that algorithm? And finally, do we trust the data's security? So do we trust that it came from a system that someone won't have tampered with? You know, a summer intern won't have accidentally written over the good data with something that's bad because they wouldn't have been allowed to. Data security, cybersecurity, and all those kind of things fall into that third bullet. Typically in the oil field, that's less of a problem for us than the first two. In terms of a knowledge worker deciding that they feel a particular piece of data is trustworthy. So that's kind of a summary of what we talked about in the first talk. And to move into the details of this particular example, some of those, well, I would say within these dimensions, in the previous talk, we actually cataloged a lot of facets inside those dimensions. And within the data source and data handling dimensions, several of those facets relate to uncertainty. So the reliability facet included things like, has the sensor been placed in the right place? Has it been calibrated? Was a reading automatically moved electronically from a sensor into a system, or did a human type a reading into a sensor or system? And those go to the reliability of that particular source of data, and obviously those all relate to measurements. In the second facet, the data handling facet, dimension, there were two facets: the origination and computations. So the origination, the key point, is it a digital reading or an analog reading? And we'll talk about why that's important in terms of uncertainty. And finally, if it's computed data, does the user of the data actually know what equations were used or what techniques were used to calculate something? And within those algorithms, does the user have access to know which parameters were used in those equations? You know, typically like in seismic processing, you know, the information to know which algorithms and what the parameter settings within those algorithms are used is typically available. But lots of the other data that's used by knowledge workers in oil and gas, that information is lost and isn't available, and it makes the data somehow less trustworthy on behalf of the users. So we're going to go through a couple of examples of this. First, we want to define what a measurement is. And there's a whole little science, a philosophy of science question around what a measurement actually is. And the earliest clear statement of what a measurement is seems to be this article from 1946, which is talking about, it's actually a psychology paper, but the definition of measurement, according to this, is measurement is the assignment of numerals to objects or events according to rules. Okay, that's too abstract to be useful, but it basically means when you make a measurement, I'm going to assign a number that's a ratio against some kind of standard. So, for example, most people know that the meter, there is a platinum iridium rod in Sèvres outside of Paris, and that is the official meter, or was until recently. And when you say something is 2.3 meters, what you're saying is this length is 2.3 of those things. 2.3 times the length of that rod outside of Paris is what 2.3 meters is. So it's a numeral, and the ratio against a standard is the unit of measure, obviously. So that's fine, and in our data management systems, we typically track that numeral, and we typically also know the unit of measure, so we know the standard that it's a ratio against. But the difficult part with measurements is what you really need to keep track of is what is the thing you're trying to measure, then what can you actually measure if you can't measure the thing you want to measure? And then, of course, where can you make a measurement? So we can think of lots of simple examples of that. You can't measure the temperature of the sun because you can't put a thermometer in the sun, but you can measure the amount of heat that it produces on the earth, and using physics calculate what the temperature of the sun is, but you can't actually directly measure the temperature of the sun. So in the world of measurement, there's a series of steps that we always go through. The first thing is to know what it is that you want to measure, and that's fine. And we normally, in data management, we normally store the desired measurement as the thing that's in a database. But truthfully, most of the things we want to measure can't be measured. But something close to it or something related to it can be measured, like the temperature of the sun. So then if I want to say I'm going to estimate the temperature of the sun based on the amount of heat that it puts per square meter on the earth, I need to then find a sensor that can measure that. I need to put it someplace. I need to calibrate it to make sure the sensor is giving the right readings. I then need to take a reading, pointing it at the sun. Then I need to convert that reading somehow into a digital value, because I'm going to need to put that into a computer program so I can do the math to calculate the sun's temperature. Then I'm going to calculate the sun's temperature. But the trick for the data management world is we need to data manage everything on this list. And typically what we would simply store is the Earth's, the sun's temperature is whatever value it is. But any error in that, any error in any of these other characteristics means that that value may be totally wrong. And users who use this information, if they have any doubt and they don't have access to some or all of these underlying characteristics, will have no faith that the value that you're presenting is actually correct. So the better of a job we can do at data managing all of these things and making them available to a knowledge worker is how we create a trustworthy piece of data so that they will have trust in our source of data. So I'm going to give a couple of specific examples that relate to the oil field in these different characteristics. So the first one is this distinction between what do we want to measure versus what we can really measure. People are sometimes surprised to learn you can't measure flow rate. Flow rate in a pipe, flow rate in a well bore, there isn't a way to measure it. The way that we measure it is by measuring two different pressures and taking the difference between them, and I'll show you that in a moment. I'm also going to go through an example of calculating water saturation. We have no way to directly measure how much oil versus water we are at a given point vertically in a reservoir, but we calculate it from other readings. And finally, we would like to know what the weight on the bit is if we're drilling a well. How hard are we pushing down on the bit to make it go through the earth? And typically, we can't measure that directly. It's always a calculation. And so we'll talk about that as an example. So the uncertainties that come from these things, again, will cause users to find any particular source of that data to be less trustworthy. Obviously, all of these things use equations. And so the first thing somebody's going to want to know across all these examples is what equation was used and under what circumstances is that equation even applicable. There are lots of war stories and examples people can give where something's being calculated and it turns out that the equation they're using is a valid equation. It's just not a valid equation for the circumstance that the user is applying it. And then I would want to know what parameters were used and in fact, what's the uncertainty associated with those parameters. So you'll see in a moment and a couple of these examples, how that fits in. But the important aspect from a data management perspective, the very most important thing from a data management perspective, if you forget all of the other things, is that if you're going to present the user with the calculated value, at least we need to save the original measurement, even if the measurement isn't easily relatable to the end value. So for example, if I'm going to calculate a flow from two pressures, store the flow because that's what the user typically wants to use, but we have to save those two raw pressure readings in case the wrong equation was used or some other assumption was faulty. Then a data analyst of some kind can recalculate what the flow should have been because we preserve the raw readings rather than only preserving the calculated result of some computation. And there's an SPE paper whose number I don't have in the presentation here, but it's a drilling system automation technical section SPE paper that specifically goes into some detail about the appropriate metadata to data manage for algorithms. The examples are drilling related, but those metadata recommendations are generic to any kind of data that we might want to move. So let's go through an example. I'm not going to turn anyone into a chemical engineer, but again, people commonly don't realize we can't measure flow. And what we do, especially in this example, in a gas field in production, is we introduce into the middle of the pipe a disc which has a hole of precisely known size called an orifice plate. We put that into the middle of the flow in a pipe. And because there's a constriction to flow, the pressure upstream of the orifice plate is higher than the pressure downstream from the orifice plate. So when we measure the pressure differential across the orifice plate and the fact that we know the diameter of that orifice plate, there's a standard ISO calculation that will result in telling you what the flow rate is. So you don't measure the flow rate directly. You measure the pressure drop. You measure the pressure drop caused by this orifice plate, but there's lots of other data you have to know, right? You have to know the diameter of the hole. You have to know the diameter of the pipe upstream and downstream. You have to know the composition of the gas and the temperature, because you need to know the gas's density to put it into the equation. So it turns out that in addition to knowing the pressure upstream and downstream, you have to know a lot of other stuff in order to be able to calculate that flow rate. So if instead of just storing the calculated flow rate, in fact, you should be data managing the upstream pressure and temperature, the downstream pressure and temperature, the assumed gas composition, which may have been based on a compositional analysis done a month ago or something like that, and then the mechanical aspects of what's the diameter and nature of the hole in the orifice plate and the pipe sizes. So that seems like adding a lot of data to the task of data management, but the truth is, if the wrong equation was used, so if the ISO 5167 equation wasn't applicable, let's say, for example, it's extremely cold outside, that equation might not be applicable. So data managing that information so that a data analyst can calculate what the flow rate actually was rather than what was reported out of the flow meter will enable them to be able to use the data. But the really key thing psychologically is that even if a user never looks at all this information, the fact that they know that it's available to them makes them trust your source of data more, because they know they could get access to that source data if they needed to. So they're going to use your value and they'll only consult that information if they literally find a problem. But they're going to doubt the source of data if they know that there's no way they could ever go back and recalculate that flow rate. Second example is a sort of reservoir engineering example. or geology example. And that is, in a reservoir, an oil, let's say you have an oil, water, gas reservoir. We normally calculate the bulk reservoir volume by saying where the oil-water contact is, and then you go up however many feet you need to before you get to the gas oil contact, and that's your reservoir thickness, the thickness of your oil column. But unfortunately, inside the reservoir, oil and water don't look like Italian salad dressing. So this is a picture of a bottle of salad dressing, and you can see that the oil, the olive oil on top, it sits above a very nice interface between the water layer below. And of course, all the spices and stuff have settled to the bottom of the water layer. In a reservoir, it's really more like this, that you do have oil up above and you do have pure water below, contaminated with salt and other spices, but in between, it sort of varies from 100% water to 100% oil over some vertical distance. So in reservoir engineering, we say at the point at which it's 50% oil and water is where I'm going to say the oil-water contact is. But unfortunately, you can't directly see that. So reservoir engineers use this equation everybody uses called Archie's law. And Archie's law says that the water saturation is a function of the resistivity of the water and the resistivity of the rock. And then there are these exponential parameters. So how do we find the resistivity of the water? We get it from a wireline log. But of course, even to interpret the wireline log, you need other parameters like the mud filtrate resistivity, the mud filtrate resistivity temperature. So in fact, to be able to get the water resistivity, you need a wireline log plus additional parameters associated with the log. To get the formation resistivity, you need it from something like RILD is a deep induction log, a resistivity calculated from a deep induction log. And then you have these exponents. Honestly, these exponents are a guess. They're just applied by experience in a particular geologic setting. And people typically use the number 2 for both of them. But if you're in a carbonate reservoir versus a sandstone reservoir, you might use a different number for the cementation exponent. Honestly, it's a guess, unless there's a lot of lab work in a particular field that those numbers are known to a higher accuracy. And then phi is the porosity, which typically comes from a neutron porosity like n phi. So there's a lot of data that goes into feeding this simple equation. And there's a lot of parameters, and you can see that some of them, there's a great deal of uncertainty associated with these exponents, for example. So there's lots of stuff to try to keep track of, in addition to knowing that this water saturation was calculated from at least an SP and N phi and some sort of deep resistivity or induction log. So there's 3 log channels plus a bunch of parameters, and then there's uncertainties associated with each of those. But to go even a little deeper than that, you could go back to the original equation and understand that the equation came from a paper in 1950 that was based on 50 samples, 20, 40, 100, 100, let's say 150 samples in 1950 is the entire basis of this equation. So there's obviously uncertainty associated with the equation itself, in addition to uncertainty of all the parameters and the uncertainties associated with the wireline logs. So the bottom line is, when a user goes and pulls a water saturation, either the depth along the wellbore of the oil-water contact, or if you've calculated a water saturation curve, there's a great deal of uncertainty associated with that. So a knowledge worker is certainly justified in saying, I need to know where this came from because I need to go and recalculate where my oil-water contact is. And the truth is, very little of this information, especially information about the original uncertainty in the equations themselves, is basically unavailable in most companies. The next aspect I want to talk about, so we've discussed the fact that I can't really measure the thing I want to measure, so I'm going to measure a proxy. I can't necessarily get access to what were the equations that were used to calculate the thing I want from the thing I can measure. And of course, the uncertainties around all the wireline logs and the parameters. The other thing that we can seldom do is put the sensor exactly where we would like it to be. So we also need to be able to know when a measurement was made, where was the sensor actually located? And the truth is that depending on the location of the sensor, a reading could be more accurate or less accurate, which obviously equals uncertainty or / data quality. Sometimes in the field, we actually have more than one measurement of the same thing. And in fact, the only way that we can tell thing A from thing B is to know which one it is. So it's customary, the standpipe pressure at the discharge of the mud pumps on a drilling rig, there's nearly always more than one pressure sensor on the standpipe because the various contractors on the drilling rig don't trust each other. So if there's two sensors and you have two sensor readings, the thing that you need to know in order to know something about them or to differentiate them is which one is higher or lower, for example, on the standpipe. So knowing where, knowing that you have data that's from LWD, logging while drilling data versus data conveyed on a wireline. These are all kinds of things that tell us about, create uncertainty in the location of a measurement. So as an example of this, here's a diagram from International Research Institute of Stavanger that talks about just one single reading that we get on a drilling rig. And that's the hook load. So when we drill a well, we're constantly pulling up on the drill pipe because if we let the drill pipe go, it would collapse in the well. So by pulling up on the drill pipe, we regulate the weight that's pushed, exerted by the bit onto the formation. So if we pull up an amount equal to the drill string, then we pick the bit up off of the bottom. And as we slack that off and let more and more and more force go down, then we're increasing the weight on the bit. So we know that the weight on bit is calculated typically from this hook load. But on a drilling rig, there's a bunch of different places that we can put these sensors. The most accurate one would be a sub or something that's instrumented that's below the swivel, and it's just right at the point where the drill pipe can actually rotate. The next most accurate one is there's often a pair of load pins that are above the swivel, maybe in the traveling block, or the various equipment puts these load pin sensors in various places, but it's above, it may be above the motor or below the motor, but above the swivel. And those are a little bit less accurate. But the truth is, we could be measuring the total weight of the upper part of the drilling derrick itself. We can measure the torque that what we call the draw works, the big spool of cable that we use to pull up and down all these pulleys to lift the drill pipe. We can measure the torque that we're pulling for that. That'll tell us the weight. Then at the other end of the cylinder full of cable, there's the place where the cable ties off that we call the dead line. That where the dead line ends in the drilling rig, there can be a load pressure cell, as we call it, the anchor. So the dead line anchor can have a pressure cell there. And even you'll see people clamp things called tensiometers onto the dead line to try to measure the tension in this rope, from which you know the amount that you're pulling up. So there's all of these different locations that we can be using to measure the hook load. Some of them are much more accurate than other ones simply by the nature of where they're placed. And of course, you have the accuracy of the sensors themselves. So it's really important, if we have something like a hook load reading, to know what kind of sensor is it and where was the sensor located. And then I make the little note here that, and if you ask the drawworks for the torque, that's typically not measured directly either. That's typically a calculation from the current that's used in the electric motor that's pulling on the winch for that. So even those readings, in this case, may be indirect. So there's a lot of uncertainty associated with where the sensor is actually placed. Again, this is information that's really important to be able to identify. If there's 6 sensors, the way I differentiate them is to know which one is where on the drilling rig. So, and of course, there's a lot of other things that we should keep track of. There's surface information like what's the ambient temperature, is it raining? For downhole information, we always need to know what's the mud weight, what's the temperature downhole, and then we need to know of those things like mud weight and temperature, for example, how do those affect a value which is calculated? So the last thing I want to talk about here is the sensor. You know, what brand of sensor is it? How accurate was it when it was purchased? What does the catalog say its operating conditions are? Is it only good between 75 degrees Fahrenheit and 100 degrees Fahrenheit? Is it good when it's cold? Is it good when it's really hot? What does the catalog say? When was it last calibrated? And finally, after it was last calibrated, the catalog can tell you that after it's calibrated, this particular sensor will drift by 1% per week or 1% per day or whatever the amount of drift is. So if you know when it was last calibrated, you can then estimate the uncertainty around that value based on how long it's been since it was calibrated. So this drift sometimes is in the catalog, or sometimes you can estimate it for a particular sensor by calibrating it repeatedly. And there's a difference, of course, between calibrating something and zeroing it. You typically zero your bathroom scale if it's a mechanical scale. You set it to 0, but that's not the same thing as calibrating the force of the spring inside of it to make sure that as you step on the bathroom scale, that the spring reacts in an organized way. One is like scale and offset. The other was just zeroing, is just adjusting the offset. So we could be data managing the original specifications and knowing when sensors were last calibrated. So of course, you know, the last step in getting sensor data is turning it into something digital. So as you know, if we use a music example, different tapes and vinyl are analog, which result in a continuous signal, but everyone knows that in fact we discretize this signal. We have a specific sample rate that we apply, and then the values that we calculate are digital values. They're not continuous. They must be either an 8 or a 9 or a 10 or an 11 in this particular example. So if I have an 8-bit analog to digital converter, it's going to have far fewer steps that I can associate the value with than if I have a 16 or a 32-bit analog to digital converter. Obviously, the more samples I take in time, in this case, along this little sine wave, then the more accurately I'll be able to represent that curve digitally. So it's exactly the same for Earth measurements and in fact describing the Earth in general. If you're going to create a digital twin of any kind, we have to put that into the digital realm. So, as I said, both the signal and its index, which in this case is time, are subject to that, what we would call a quantization error. So a CD, for example, music CDs, it's 44.1 kilohertz. Wireline logs are typically a half of a foot sample interval. So every 6 inches. If something happens between there, you won't know about it. And then if you think about reservoir simulators, we're going to say that the area under the Earth is broken up into a certain number of cells, nominally cubic cells, and that's how we quantize the Earth for purposes of doing reservoir simulation. All of this is taking something which is fundamentally analog, which is to say it changes continuously, and converting it into things which are set to a particular value over some particular index. So obviously, all of this leads to uncertainty by the fact that I have converted a continuously varying thing into these blocky digital cells, if you will. So knowing something about the analog to digital conversion process is also really important for measurement data. And then just like the sensors are calibrated, it's worth noting that analog to digital converters are also calibrated. Sometimes modern instruments tend to be called digital instruments, but of course inside the digital instrument there's an analog instrument which is tied together to a digital or analog to digital converter, but those may be packaged as a single instrument. So it could be the calibration process actually does both. It's calibrating both the analog device and the incorporated A to D converter, but sometimes in the field you'll find that those are separate pieces of equipment and they need to be calibrated separately. But it's more data to manage. The activity, the maintenance activity of doing those calibrations are what knowledge workers need to know if they are doing something that requires high accuracy data to feed some computation. So again, data managing those maintenance activities, those calibration activities, whether they're done in the field or in a lab or some outside shop, are important for us to be able to data manage so that the users who use the data will trust your source of data. And again, users won't always consult this information, but they trust a source of data that they know makes this information available to them, that they could use it if they needed it. So to summarize, all of this data and all of this other information that we call metadata are valuable for analytics. And parenthetically, focusing on that metadata and how we manage metadata in general, not just for measurements, but for all kinds of oil and gas data, is going to be the subject of the third of these 3 talks. But all of it's obviously valuable. If I give you a water saturation, if I just tell you the depth of the 50% oil water saturation line, and I'm a reservoir engineer and I think that's totally wrong, I need to have access to know what SP, RLD, and NFE curves were used, and what were the cementation and saturation coefficients that were used in the Archie's equation, if Archie's equation was used. I need access to that so I can say, oh, well, those they used the wrong parameters because we're in a carbonate instead of a sandstone, or whatever the specific case is. So somebody who needs to sharpen their pencil and do a better job of predicting something needs access to all this information. The raw measurements for sure should be saved because that's what the company paid for. The calculated data makes it easier for the user to not have to constantly recalculate it, so we persist those calculated values. But the raw readings is really what the company paid to acquire, and if we throw those away, then we're throwing away the things that were funded. And then, of course, we need to keep those calculated values, but also don't forget, because of Sarbanes-Oxley and for contractual reasons, if we make a decision, like a decision to drill a well, a decision to declare a field commercial, decision to drill an appraisal well, whatever, a decision to plug and abandon a well or a field, whatever those decisions are, we need to preserve the computed values as they were at the time those decisions were made, because I may go back and recompute things, and maybe there's a new equation that does a better job of calculating something. So I go back and I recalculate something to have a better idea of what the reality is, but I made a decision 6 years ago on the old equations that we're using. So we need to be able to keep those computed values on which we base decisions. And lastly, the challenge to data management kind of people is a lot of the data that we're talking about isn't coming from the sources that we're used to working with. The calibration activities, installation activities, a knowledge of where things may be located on a piece of equipment are possibly in a maintenance system. The maintenance management systems that either come along with your accounting system or from standalone maintenance management systems. A lot of the real-time data information is available in a rig site data acquisition system. So typically, that's going to be available in OPC DA or OPC UA on a rig site control system, and then of course we would move that data via WITSML, back to the office. So either via OPC UA or DA or via WITSML, you should be able to find a lot of this information as to the state of sensors and what their raw readings are and what the calculated readings are. The specifications that were used when equipment was purchased should be able to tell you the actual sizes in addition to the nominal sizes. That's how you can find out how much a sensor drifts after it's calibrated. And of course, the equipment specs in the sense of the drawings that came from when a piece of equipment was installed will tell you where it's located. The procurement department actually are the people who are going to know what was actually ordered and then what was received, because sometimes what's received is a substitution for the thing that was ordered. So just because something was specified as a particular kind of piece of equipment, you can't assume that's what was actually installed, because the vendor may have substituted something because they were out of stock on a particular thing. And then the procurement department, of course, knows when stuff was actually bought. And then finally, and lastly, to get to those questions about uncertainties in equations are papers. So I was showing from Bolton of the AAPG, the plot from when Archie's equation was first developed in the late 40s and into 1950. And people are going to need access to those original papers to be able to understand how uncertain is the correlation upon which the values were based. So with that, in summary, obviously we want to transfer the data using public standards so that people understand what's in the data. We want to manage the raw readings. We want to manage the metadata about everything to do with acquiring and computing those readings. And this information is what would enable a knowledge worker to assess the uncertainty of a piece of data. The fact that they can access this data will cause them to trust your source of data, even if they don't need it. But when they do need it, it's going to be essential for them to have access to this information to be able to recompute something in the event that it turns out that some assumption might not have been correct. So that's how you're going to build trust in the data store that you run, because you're producing data that the users feel is trustworthy. So on that, Phil, I think I'm going to end.
Thank you very much, Jay. As always, fascinating content. And indeed, raising so many issues, I think that people often are sort of subconsciously aware of, but have never really walked themselves through in such an articulate manner, how you go from just being a bit uncomfortable about data to actually rationalizing where the discomfort or comfort may be, and how you can implement that in a more structured way going forward. Now, I don't know if everyone is familiar with how our conferencing system works. At the bottom of your screen, you have a little box called Q&A, question and answer. You can type in here questions to Jay, to Jay basically, and we will then answer them in sequence of question. So if you could take a minute to put any question to Jay, that would be most welcome. Now's a good time. You have him online live. Maybe while we're waiting for the first question, Jay, you could say a few words about how this notion of trust in data is embodied in the standards, the data assurance object.
Sure. So the current generation of energistics standard, so that's basically any version 2 point anything of WITS-ML, PROD-ML, RescueML, now is able to carry from a producer to a consumer any of this kind of metadata. So you could, if you chose to, when you transfer data from one point to another, completely describe the sequence of activities that were used to calculate that piece of data with all the parameters and all the names of all the software and the names of the algorithms. And, that would be a really heavyweight data transfer to be doing in real time, but the standards allow that now. And in addition, the standards also anticipate supporting a kind of a workflow that the industry calls data assurance as opposed to data quality. So I was saying in the beginning that, completeness or some judgment of quality isn't really what people use in reality. In reality, people, knowledge workers, need to be able to decide whether a particular source of information provides data that's suitable for the purpose they want to put it to. And a trend, at least among some of the large operators, is they create internally in their companies some sort of a policy around data quality. So you could have a well surface location quality policy. And you might say that every well needs a latitude and longitude, and every well needs a X and a Y in the local map projection. Every well needs a name. Every well needs to be resurveyed within 30 days after the well is completed. Let's say you have a policy that consists of those rules. If I send you a piece of data that represents the well location while the well is drilling, it would be really good for me to know that the data I'm sending you conforms to all those rules except the last one, because since the well hasn't been completed yet, it hasn't been resurveyed. So what you really want to be able to do is tag that piece of data with a little piece of knowledge to say that the data I'm sending you is the best data we have, but it fails the fifth rule in your policy, which is that the well needs to be resurveyed. So all the second generation of the energistic standards now enable you to move these little data assurance tags, and they're designed so that you should only send them, of course, when data fails a particular rule, because when you're moving data from an acquisition company to an operator, or from one operator to another, or within applications within your company, or from an operator to a regulator, you expect that the data is going to conform to all the rules. So it's really only noteworthy to remark on when a piece of data fails the rules. So that's the purpose of this new little thing called data assurance. It's just a little tag that comes along with the data to say that here's what we have, but the sensor hasn't been recalibrated in 6 months, or the ambient temperature outside is 120 degrees Fahrenheit. So the sensor might not be giving a good reading, or whatever those things are. We're now able to pass that out as a little external tag that comes along with the data transfer.
Understood. And I think a lot of times people tend to focus a bit too much on the fact that it does indeed take some programming and process effort to implement these things. But down the line, in the months and years ahead, it saves a huge amount of time for the people actually putting the data to work. And as we know, data has longer and longer life cycles. We're often using data that's 10, 15 years old in field studies, in regional studies. And the absence of this information is a huge burden on the people having to put the data to work. Because in the absence of formal codified information, someone has to do the homework all over again. And these are things the industry, I think, going forward needs to be thinking about in the greater picture of digital transformation and the application of analytics and all these good things. Is without this information, there's a lot of basic work that goes in before data can actually be put to use. Still not seeing any questions. I think basically you must have just floored the audience and all good. So we're going to close this webinar. As I mentioned at its opening, it is recorded. It just takes us an hour or two to put it up on our website. So look out for it, I'd say, starting tomorrow, Friday. Look out for the announcement for the next and final chapter in this Odyssey on trust in data. Thank you, Jay, again, for your valuable insights. Thank you, everyone, for your time attending this. And without further ado, we will close this webinar. Thank you and have a great day.